start on time, so probably people keep on joining. How's everyone?
Good, sir.
I see Jose, I see Varun. So I guess just three of us here. Krista is joining in as well. All right. Hi, Krista. How are you?
I think she's still connecting.
Oh, she's still logging in. All right. So let me first ask, how is your KPR going to progress?
Well, I finished it last night. I was wondering if I could also get some feedback on that.
Okay, since I've updated the deadline, I'll be looking at everything at the deadline.
I'm
But
sorry, say that one more time, sir.
yeah,
You
so
cut out.
if you had posted a question in discussion group, of course, we can discuss it there.
Oh, okay. And then
Yeah.
discussion.
But once you have submitted the KPR, then I wait until everybody submits, and then I can go through from one side. But if we have discussed the selection of paper, you should be okay. Yeah, that's my experience. Students who discuss the idea, they always have 2, 3 iterations, and we end up finding the good paper for that exercise. So hopefully we have done that.
Okay.
So, all right, so let's get started. We are in module 2. Today is Friday, and these are our goals for this module. I think we have, I have shared the, what do you say, soft chalk lesson, which covered many important manufacturing processes for semiconductor devices. I know there are limitations and how much can we interact on those, but that's something where we will, I'll have a couple of micro lectures posted today. I didn't want to bombard you with too much information, just wanted you to have that. In there, we had a quiz question about oxidation also, which is the natural process where oxide interacts with metals and creates what we call as rust. But in our case, when we talk about silicon, we deliberately create that oxide because number one, it is easily grown. You can control the thickness of that oxide. Number two, the oxide is very different in electrical properties than silicon. Silicon can be easily made to be conductive by introducing known uh, species like aluminum or boron with what the process what we call doping. But silicon dioxide is a very good insulator. So when we talk about computer chip, we have uh, transistors, capacitors, resistors, all the things that you would put on a breadboard. But when you make integrated circuits, we are taking all the breadboard uh, individual components and putting everything inside silicon. One might say, why are we studying about silicon processing? So the reason is, and I'll show you a few examples today, silicon industry or semiconductor industry or what you call electronic industry has pushed the miniaturization of devices over 3, 4 decades. They keep on pushing to make chips or components that go on those chips smaller and smaller. Hence, they have gone into what we call as nanoscale region. Now, that industry has resulted in making equipment, processes, many what you call characterization equipment for that industry, which has helped us in what we generally call nanotechnology now. Because nanotechnology is not anymore only about devices, but devices, processes, and all the good things we have learned from silicon industry has helped us in overall nanotechnology. So that's why we study a bit background on what we call as solid state fabrication, or more precisely silicon. But silicon is not the only semiconductor material we use. There are many, many more semiconductor materials that we use. But we focus on silicon because if you understand this, it's very easy to understand the others as well. So these are the learning goals for this module. So I hope we have went over many of those. Now, when we are talking about that, we have got the processes from semiconductor industry. It took many years or many milestones before we got here. So this slide, can you guys see my slides? All right. So this slide gives us a little bit history. This comes from a book as well. And if any of you are looking for these books, let me know. I might have soft copies of many of those books. Now, this is where, if you see, there are milestones. We had the development of radar, which was World War II. And what they did was they started developing pure semiconductors because the radars, at that time, it was called, they used to call transistor based things. So radio, even radios, they used to be vacuum tube radios, and then there was a big thing they called transistor radio. The idea was those things were using semiconductors because now you could use transistors in those. So Richard Feynman's paper came in 59, and 1960 we started planar batch fabrication process. So planar batch fabrication is that they would get silicon and they would build everything on top of it. So I know you guys have read up on Feynman, and it's very exciting, but Feynman's talk was not done in isolation from the actual industry, the things that we're working on. So Dr. Feynman was aware of things that were happening, and he was aware of, if you read that paper, many of the things were already happening at that time. But of course, not at that vision or that scale that he identified. And then 64, we had the what you call MEMS devices. We'll talk about that next week, micro electromechanical systems. Every device we have, with even the cell phone, which seems there is no moving part inside, but there are moving parts inside what we call as MEMS devices. So moving parts, very small motors, very small gyroscope, which has moving parts in it. So they're all, overall, we call them MEMS devices. So they were built as early as in 64. Microprocessor came along 1970. We'll look at a little bit more on when the original, the first couple of times it happened. Or our accelerometers are all MEMS devices. We have accelerometer in everything that moves. Cell phones, cars, even garage door. Any movement that we want to measure would be there. In industry, they have, we have all the way from gas industry where they have uh, offshore rigs, which are standing in water. They want to measure their uh, stability. We have accelerometers. Eric Drexler is another visionary, sometimes controversial, but nevertheless, he is another gentleman who has pushed lots of exciting or revolutionary ideas for nanotechnology. Some of you talked about scanning tunneling microscope, which they say is directly the vision of Feynman. Yeah, so they got Nobel Prize for this discovery, this device, not discovery. This is an instrument that can measure things at nanoscale on surfaces. So if you keep on following, buckyball is another major discovery. They got Nobel Prize for that also, which are 60 carbon atoms placed in the most compact form together, and the most compact form is the form of, uh, sorry, is the form of a soccer ball, like soccer ball, football as it is called in the rest of the world. That's the shape of what we call a buckyball. So the hardest material, as they say, because there's no more, nothing more compact that you can bring atoms together. So that was 1985 atomic force microscope. It's another major discovery, major development, which can again look for materials on a surface and which can measure how things are at ato- atomic scale, atomic level. So that was 1986. Carbon nanotubes, some of us have studied that also in their first homework. So these are all the things that have happened over years. Now, where are we today? So there are so many applications. Some of them are already evident. Some of them are in experimental stages. But the vision of nanotechnology, or the what do you call that? The available equipment, available material is making it happen. We have fibers which are stronger than spider web. So when you say spider web, if you think about the how thin it is and compared to its strength, it's a very, very strong material. We're looking at metals stronger than steel, less weight. We're talking about reactions, and we discussed that in one of the Media's point question about surface to volume ratio. We can cut them, break them into smaller pieces, so they have very high reactivity. We have polymers that are conductive. Conductive polymer is a major thing now. We have coatings that can change the surface, whether it's, so in simple terms, hydrophobic, hydrophilic, but for industry, we want to make those things frictionless. Those who might have served on in military, they know many places where we want things to be frictionless so they can move faster. Ships, aircrafts, uh, even trains, even the what do you call it? Shipping on ground and the on water, they all require those kind of things. We're looking for materials that can adjust to their surroundings, material that can repair themselves, they can clean themselves. Look at some examples today. Powders, 5 times as light as plastic, but give good protection like metals. So these are just few things that have already happened or they are in testing phases. Medicine, we talk about medicine. There is, from cosmetics to actual diagnostics, there is lots of work that's going on. There is there are not just early diagnostics, which can, in many diseases, help people get care, get medication, which can overcome that disease, for example, like cancer. But there is also a new paradigm where we, instead of looking at the whole tissue, want to look at few cells, what we call as ability to view cells in vivo. That we just want to look a few cells and look at their behavior, because if you can control them, you can control the whole system. We are injecting things in ourselves. We are using nanomaterials to create new pills that can release the chemicals according to the time scale we want, or according to an external stimuli that we want them to trigger the release. We are growing, we have grafts, right, which are biocompatible, and they can regrow bones and organs much faster. So there's a whole range of things. Somebody asked last time about nano whiskers. So it's nano whisker is just an example. The idea is that there's so many uh, chemicals that we can create to our will that can have hydrophobic properties. And if you coat a hydrophobic material on anything, that can impart the hydrophobic nature to that underlying surface. So that was the idea behind what you said, that clothing that doesn't get wet, right? Oh, yeah, this is the example. From clothing, can talk about even the coating, right? So coatings on glass, for example, that don't get wet and don't get dirty. All right, so anytime we can stop me, ask questions, we can take stock of homeworks. I had graded homework, the first homework, and I did my grading and my corrections on the PDF itself. So if you go and look at the PDF, you'll see if there was any mistake, any grammatical error, if I had some comment, that's posted on that PDF that you had uploaded on Blackboard. Did you get a chance to look at those? Jose, you're muted.
No, sir, I didn't. You uploaded the corrections on Blackboard?
So,
Or
the file that you submitted,
yes, sir.
I put the markings on the same file.
Oh, on the same actual file. Okay.
Same file. So when you go back in Blackboard, you can download that file with my markings on it.
Oh, I see. Okay. Thank you, sir.
But I don't put the grade, because for the grade, there's a rubric, and I just click the rubric points, and it automatically calculates the points that you would get, because if you have followed those requirements, the rubric will take care of those requirements. And the rubric has 5 points, and it's posted. You should have been able to see the rubric when you were submitting your homework. Do that for your homework too, and for your KPR also. Look at the rubric, make sure you have addressed all the things that are listed in the rubric.
All right.
Rubric helps me stay fair with everyone. That's the whole thing about rubric, right? I read it, I put my comments, I make notes, but then when I'm grading, I just go with the rubric to make sure that, for example, there is one point in rubric where it says, okay, have the student used 12-point aerial or used one page. And if you have missed one of those things, so that will adjust its grade from 0 to 1 to 2. 2 is maximum for one category. Then maybe there's another point for grammatical mistakes. If there are 0 mistakes, you get 2 points. If there is 1 to 4 mistakes, then you get, I think, 1 point. If there are more than 4, then you get 0 points for that rubric point. So I put markings on your submitted file, but on the right side, there is a rubric for me where I just click, 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 and that automatically gives you the points for that assignment.
Okay, sir. I'll look at it right after this
Yeah.
lecture.
So this is for all of you. So I know some of you have asked me questions about why did you get more or less grade. Look at the rubric and we can discuss that. Right? So everybody's good for the extension and the deadline, and we want to make sure we get those things in time so we can move to the next week. All right, so now there's the applications keep on going for nano applications, but let's get back to the idea what we were talking about. Why do we learn solid state fabrication? So devices, the most fundamental of devices is a transistor, right? So transistors were invented in 47, but it was a group of people who came together, and transistor is a kind of a resistor, but you can control the resistance by a third electrode. So, you know, in resistance, you need 2 electrodes, right? So you put those electrodes and you measure the resistance. But if you use a third one, adjust that resistance to be high or low. When you make it higher and low, that is the digital thing, right? 0 or 1. So high voltage, high current we call as 1, low current we call as 0. So it gives birth through digital idea. So that's a blown a version of actual transistor that they made, which is placed in a museum somewhere. Now, from that, then they came up with the idea of integrated circuit. And that was the homework too that you have studied, which talks about history and a little bit of what started the applications that we have. So the very early uh, transistor was something like this, but then we have seen that 2, 3, 4 iterations, and today it's just a black box, right? You have the integrated circuit that we put in our circuits, that which has, if you talk about processing units, they have billions of transistors in there. But this is where they started. Now, another thing that happened was taking that transistor and putting it into an integrated circuit. So this was what happened in Dallas, Texas Instrument, where they showed that you can put everything in a planar way. And this the right hand lower side. This is the actual picture of this lab notebook from Jack Kilby, and he got Nobel Prize for that idea. He shared the Nobel Prize with Robert Noyce, I think. So Robert Noyce was another gentleman which you must have read in that homework 2 paper, who's considered to be what they call mayor of Silicon Valley. So he was co-inventor of the uh, Intel as well. Now, this having one transistor or bunch of integrated circuit components on one layer, now when we move forward, we're talking about multi-layered chips. We talk about integrations of so many billions of transistors and components together. This is an old picture, the one on the right-hand side, but it shows you the complexity, the levels of different circuit levels inside an IC. This is an SEM picture, scanning electron microscopic picture, which shows you just 6-level copper interconnects, which everything has been dissolved, etched away to show the detail of copper that remains. On the left-hand side, if you see this picture, so that's just showing that these copper wiring are made in silicon. Silicon is where you would have made devices. What is the current status? We are making billions of transistors on one chip. So you guys have seen chips, right? Computer motherboard, you know where is CPU. So CPU is, if it's general purpose, we call it CPU, but if it is focused on graphics, we call it GPU. You guys, many of gamers know about GPU as well, right? Which is dedicated not for general purpose computing, but only for graphics computing. We have billions of transistors, 54 billion in this thing called Ampere, which is a GPU by NVIDIA, right? You guys know NVIDIA? Gamers know NVIDIA. Gamers know Ampere also, which is top of the line GPUs. So this is made on 7 nanometer technology. So 7 nanometer means the transistor half length, the channel length of a transistor is 7 nanometer. Source and drain are so close that now how do they make those 7 nanometers? All the steps involved are what you have in soft chalk, some derivative of those processes. Because, yeah, soft chalk, the lesson on the silicon fabrication talks about basic processes. But when you go to such a small size, we have to make many modifications to that process. For example, they don't use optical lithography because light cannot cut to that small resolution. So we use electron beam. But nevertheless, it's the same lithography process where you have a coating of a material and you shine electron beam and you make the features and then you wash it away. But in soft chalk, we talk about optical lithography. So we do the coating and use the UV light to remove the material. When we talk about next generation processors, that we'll talk about e-beam lithography. So now it says TSMC. So TSMC made this chip. Anybody has a guess where is TSMC located?
Texas.
Texas?
Taiwan.
All right. Anybody else want to take a shot at where is TSMC located? You guys want to Google that? What? Just type
Taiwan.
Taiwan Semiconductor Manufacturing Corporation. So we are not alone. There are other places who are making these things. So think about it. That is the status. But we didn't get here overnight. This
Sure.
is example of an Apple A8 processor. What processors are they using now in Apple product in iPhone? Is it A11? I guess,
Oh yeah.
right? So
Sir, what country would you say is leading semiconductors?
design, fabrication, sales. So there are all different ways how you would look at it.
Oh, and maybe in design.
Design is still United States.
Oh, okay.
Yeah, because the major push is coming from here. But when you talk about manufacturing, yeah, so these are still Far East. They make those things for us. But they
Mm.
make those things that are top of the line. So technology, Isaac, are you okay? Oh, I saw you at how's that going? All right. So, but if you think about it, this die is 8.5 millimeter by 10.5 millimeter with 2 billion transistors, right? So, of course, our cell phones are not doing GPU kind of work, but still they have 2 billion, 2 billion transistors. In what size? In less than a centimeter by centimeter, about centimeter by centimeter. So that's the kind of, that's the reason you want to study solid state fabrication before we talk about nanomaterials and all that. And if you open this thing up, you see, now this is Qualcomm processor here. This is probably another cell phone. You have a whole bunch of processors, accelerometers, antenna, RAM, things that are integrated together on that one circuit. So that's the kind of production which has given many tools or processes or characterization tools for metrology to nanoscale engineers like us. And this is again result of visionaries of people like Moore. So this is one thing which has kept the semiconductor industry on their toe. We call it Moore's law. So he wrote in a paper in 1965. It was not even research, but it was just in a magazine because he's one of the co-founders of Intel. And he said that by and he was citing for 10 years. From 65, he's saying in 10 years, we'd be squeezing as many as 65,000 components on a single silicon chip. So when you put that in context of those 10 years, it came out that every 18 months, the number of transistors, the number of components would double. That was what you call as Moore's law. Every 18 months, the number of components would double. What we have then called as Moore's law, and industry tried to keep up with that for years after years after years. This is an old picture, you may not even find it now, where the plot, now if you see x-axis is years, right? Straight linear, but y-axis is log plot. You see that? It's going from 1,000 to 10,000 to 100,000 to, so that's a logarithmic plot, which is with depicting that idea of doubling every 18 months, kept it at a straight line. But there is so much you can do with silicon, or there's so much you can do in that small scale. Because a time comes when you start messing up with the uh, gonna throw this word like movies. When you start messing up with the quantum states, we'll talk about that later on, but right now we can just think about it that you make them so small that we start messing up with atomic structure. We start messing with the uh, electronic properties of materials. So the devices cannot operate or behave the way we want. So then what we have done is we we have kept on shrinking them, but there is a number given 30% every 2 to 3 years. They became cheaper, they became faster, but they the new issues started coming up, which was about how do you connect them? How do you wire them? How small do you make that if there is an insulator that doesn't let any electrons pass through it? But we became so small because now the electrons would tunnel through that. So we had to then change materials. We, instead of silicon, we have started using hafnium dioxide, for example, in those spaces. But then industry took a step back and said, okay, we'll talk about that later on, that instead of putting them so many together, why can't we make them in parallel? Hence the concept of multi-core chips came through quad core. You know, we know quad core components, quad core CPU. So those are a bunch of things that happen to keep up with that demand of making them faster and faster. So here it says scale factor is a factor we use. It is, we use it at square root of 2. So we multiply and that gives us how you can keep on pushing things smaller and smaller. All right, so I use here, let me go back. So here we use this word 7 nanometer technology. So this is what we call as technology node. What it means is that what is the current usage of uh, current size of the chip. So we call it technology node, but it has a very specific meaning to it, which is it's the minimum half width, half pitch of the metal interconnect, which would represent the process capability, enabling high density ICs. That's what we call as the technology node. So minimum half pitch of custom layout metal interconnect. What does it mean? So pitch is how often can you repeat something, right? So you put a transistor, then you cannot put another one too close to it because they would start interfering with each other's operation. So we take that distance, then how close can we make minimum? We take the half of that number. So that's what we call as technology node. And whichever is the smallest that we have. So this is an example of 35 nanometer memory device. And you can see that these numbers are real. You cannot make say something if this is 35 nanometer, then next thing that you make has to be further away. Otherwise, they will start interfering with each other. So here is 45 nanometer node. So these are the specs that we take from the actual fabricated device and how close we can put them next to each other. So there's lots of simulation goes in what we call as VLSI people who do that. And technology node over years we have been pushing them smaller and smaller. And that basically gives the whole industry follows those numbers and they try to catch up with each other on to following to get to those numbers. So this is again uh, some history on that. Can you see my slide? Sorry, I think I pushed the wrong button. So you can see here's TSMC that announced that they would start production in 2018. So now they are doing 7 nanometer production. So when somebody tells you 7 nanometer node, all it means is the half pitch width of those interconnects. How close can we make those things to each other? All right, questions? All right, so let me.
So
Okay.
I have a question.
Yeah,
Why do they consider like half of the node? Like, why not call it like a 14 nanometer technology?
yeah, they just became a standard.
Oh,
Yeah, so they,
like just by convention.
yeah, so the thing is, the what you call ITRS, it's an organization. It's not all manufacturers, different market players. They come together. They have representative, and they agree on some common numbers with each other. So
Okay.
the thing was that every company was using its own measure of how they would scale things down. So there's a long history behind. So they agreed on, okay, this is what we'll use to define the node or what size of devices we are making right now. And the interesting thing is each one have their own processes of how they are achieving that node. They don't share it with each other.
Right, right.
So, but they share, okay, this is the standard we'll use to tell you what node are we at.
Right.
Right.
Okay.
So I'd like to share this video. Let me see if I can get this up. All right, hold on. All right, you can see this, the video. Here's, all right.
SIA is really a very interesting trade association that brings fierce competitors together and very effectively collaborate to take on some of the biggest challenges.
There are certain things that can only get done at the SIA.
Semiconductors have been a foundational technology that have gotten the world where it is today.
What I really love about the semiconductor industry is you're really building something. You can actually hold your product, you can see what it does.
Life is totally dependent on technology.
Our cars are going to get smarter, they're going to get safer, our homes are going to get smarter and more efficient. Medical technology is going to be less invasive and lead to better quality of life.
The semiconductors that we're building are ending up, as the brains or the center of, this interesting, new world.
It's been driven off of basic research. It's been driven off good university education system.
Research has been at the heart of what lets us do what we do.
We just celebrated the 50th year of Moore's Law.
Today we're in the 10, moving towards 7 nanometer range. So we are approaching a limit because we're getting down to atomic dimensions.
One of the big things that we're driving towards now is doubling down on R&D.
The SIA, by collecting all these companies together, is able to make sure that we have a voice. Now we have influence on policy for things like promoting innovation.
Human-related issues, how do you get immigration in the right place? How do you get people interested in the industry? How do you get R&D to flow from the government into universities? Because we have this very unique asset in the United States. How do you keep that going?
Whether it's in education, whether it's in policy, whether it's in research funding, we are more powerful together than we are individually.
Each individual person may not be big enough to move the needle, but together we can.
My view of the future, not 5 years, I'm thinking 10 years, 20 years. This is a core technology that needs to continue to help.
The real sort of challenge for us as leaders is to figure out how do you make that something that matters to people.
What's good for the industry, what's good for the country. And that ability to come together, I think, is one of the great attributes of the Semiconductor Industry Association.
All right, so that's why.
So we've already hit that 7 nanometer limit, right?
Pardon?
Or we've already hit that new 7 nanometer standard, right?
This video was from 2017.
Okay.
That was about the time when they were hitting 7 nanometer. And now the products are out. All right, so this is where this the end message for today. The disruptive technology computing that has enabled us to keep on pushing, making equipment, making not equipment not just to manufacture but also to characterize, which is leading to this whole new range of activities and products across so many things at nanoscale. So let's stop here for today. Questions? All right, so one thing you can talk about, we can have a KPR homework too, and we can do anything related to material today before the deadline, not after the deadline.
Dr. Iqbal, I have a question.
Yeah.
With the new extensions set in place, when do we have to turn in the recording or the presentation for the KPR?
KPR, that will come afterwards. So today, yeah, that will be a separate deadline for that. Right? So once I have everything, probably on Sunday, then I'll figure out how we can do this.
Okay. Also on my homework, I noticed that there was a there was a big X on the, because I added another page for citations. Do you just
yeah?
I added another. Do you just not want that, or it's just solely just one page?
Okay. Okay, guys, you submit how many pages when I ask for one page?
One page.
One page. Big, bold, one page. That's it. That's all I would take. I won't even look at your any page, which may be number 2, which may be number 3, which may be, because one page. And simple reason, I'm not trying to be hard on you. I'm trying to be fair with you. I'm trying to be fair with everyone in this class. And my fairness dictates that I have to give level playing field to everyone. Level playing field means that each one has to have exactly similar circumstances, whether that's technology, whether that's use of technology, whether that's number of pages. Hence, I don't even look at more than what was expected. Mark, does it make sense? Okay. One thing that may be troubling to all of you, 1 point here, 1 point there, don't even worry about it. At the end of the day, if you say consistently keep on delivering, you'll be okay. I can promise you that it takes lots of lost work to fail my course or to get bad grade in my course. As long as you stay on top of simple things, yeah, a point here and there will not bring you down. All right, take it as a promise, take it as an omen, take it as a, I don't know, my brotherly advice that don't worry about a point here and there. All right, Mark?
Yeah, understood.
Very good. All right, another question.
So I was just looking at this, like the 7 nanometer. I was just wondering, like, what devices are out for the 7 nanometer technology.
GPU.
And like a news came in from the Google like 18 hours ago that they're saying all the 7 nanometer technology, Intel's 7 nanometer technology will be delayed till 2022 or 2023.
Intel is delaying that? Wow. And TSMC has already rolled it out. Yeah, and this again, COVID-19 is going to change those things as well.
Why was it delayed?
I think it's the people. It's nobody's buying anything.
Oh,
Okay, so it's the demand and supply on those things.
In the news, they say that Intel's the way they are getting the 7 nanometer technology, it's broken. It's not working. I think that I'm not sure like how exactly. I didn't read the entire article.
Oh man. Yeah, I have one of my students. He did PhD with me. He is working for 2 years. He's working on 4 nanometer technology in Santa Clara in California. And I went discuss it with him how they do what they do. But yeah, they've been working on 4 nanometer for a while. Of course, they work in-house to perfect the technology before they can make products and send them out. So 7 nanometer, so it means Intel has lost the race to 7 nanometer for now. But yeah, this is so this SIA, the video we looked at, yeah, so they come together and they used to give out very aggressively ITRS, International Technology Roadmap for Semiconductors. So SIA used to give out ITRS, which used to define that by next year RAM has to have this technology, the processor has to have this technology. That somehow has shifted from defining the sizes to defining the capabilities they want, like clock speeds and all that. But we'll talk about it some other time. Today, I just wanted to focus on uh, why we are studying solid state fabrication. How does it relate to our topic of our course? All right, questions, comments? All right, very good.
I'm saving them for the discussion.
Yeah, sure. On the discussion forum, right? Yeah. So it's another thing. Office hours. I was told that what we do here on Friday, it's not part of asynchronous. So I said, okay, we'll call it office hours because this is where I want you to come and talk, and we can do this here as well. Because they somehow technically, if we do an in-person session, then the course is not asynchronous, some classification or something. So I said, okay, this is an office hours. But we'll do this, we'll keep on doing the same thing, what we are doing right now. All right? All right, no question, I'll let you go to your weekend.
Thank you.
All right, take care, everyone.